Okay, what we're talking about is going to be working with a lot of problems with integers and a little bit with decimals and remainders, kind of. But we're going to start out just talking about multiplying positive and negative numbers with integers is generally what we're dealing with here. And my assumption is that we're all pretty comfortable with the idea that a positive times a positive gives us a positive. Um, That's probably a pretty comfortable idea. But a positive times a negative is a negative. While you're probably okay with accepting that, I want to give you a couple of ways that you could think about it, a couple of ways that you might explain it to somebody down the road. Let's just say we wanted to do 5 multiplied by -3, or 5 times -3. One way we could look at this is as repeated addition. So instead of 5 times -3, that's, well, -3 plus -3 plus -3 plus -3 plus -3. So I have 5 -3s. This 5 times -3. And well, now adding these, you could use a number line for this if you'd like, and maybe start here at 0, and then we go -3. So that puts us here at -3. And then we do -3 again, puts us at -6, -3 again, puts us at -9, -3 again, puts us at -12, -3 again, puts us at -15. And sure enough, we can see that 5 times -3 is going to give us -15. And that's a way of looking at the idea that if we take a positive, multiply by a negative, the result that we're going to get is negative. Another way that you might describe positive times negative is just sort of using a pattern. And what I mean by that is if we were to say that 5 times 2, well, that would be 10. And then 5 times 1. So we dropped it down by 1. Okay, that's 5. And then 5 times 0, well, anything times 0 is just 0. And then 5 times -1. Well, even if you don't know what 5 times -1 is, you could just follow the pattern here and see that we went from 2 to 1 to 0 to -1. And then over on the right-hand side, then it went from 10, went down by 5, it went down by 5. So this is going to go down by 5 and result in -5. And here again, we can see a positive times a negative gives us a negative. So it's just a way to sort of describe why that's true. Most of you are probably very comfortable with the idea that positive times negative is negative, but here's a couple of ways of looking at why that happens. Let me know if you have any questions or anything related to that. Okay. I did leave one out, and that's negative times negative is a positive. This one can be a little harder to explain. I'm gonna sort of show you 3 different ways that you can kind of think of this or use it to explain. And any of these you might like, you might not. It's okay. That's why there's some variety here. The first one is probably the clumsiest of the 3. And it's if we think of -3 here as being the opposite of 3. If we just kind of say that that's the opposite of 3, which it is, remember, opposites have the same absolute value. So 3 and -3 are opposites of each other. So -3 would be the opposite of 3. Okay, hopefully we're all good with that. And if I were to write this, -3, well, what we've got here then is we have the opposite of 3. And well, the opposite of the opposite of, that takes me right back where I started. So that's just going to be 3. In essence, when I have these 2 negatives next to each other, they quote unquote cancel each other out because we're doing the opposite of 2 times. Okay, how does this work for multiplication? Well, if we wanted to do, say, -4 times -5. Now, I understand you would never really practically write it this way, but just as a way of explaining this idea, let's just say we wrote this as negative times 4 times 5. Okay, well, what we've got here then is The opposite of the opposite. I'm doing the opposite twice. It's like turning a light switch on and then back off again. The opposite of the opposite, well, those just sort of cancel each other out there, and I'm left with 4 times 5, which is just 20. And what I've done here is negative times negative gave me a positive result. That one's not too bad. I think you're playing a little fast and loose with notation and the way we write things down, but it's not terrible. The opposite of turning a light switch on and off takes you back where you started. It isn't a bad way to go here. We looked at using a pattern before. Let's look at that again. So if I want to say 2 times -3, that would be -6, because at this point we're comfortable with the idea that positive times negative is negative. We're going to do that first before we build up to this one. So 2 times -3 is -6. And okay, how about 1 times -3? Well, that would be -3. And then 0 times -3, anything times 0 is just 0. And here we're building our pattern, similar to what we did before. I went from 2 to 1 to 0, so the next thing down here is going to be -1. And I'm going to see what happens over on the right when I do that. So when I go to -1 times -3, and I look at the other side of this for the pattern, -6 got bigger by 3, got bigger by 3, that's going to get bigger by 3, and I'm going to have a positive 3 over here. And I think this way is a very good way, the pattern recognition way. You might like the what we did over here on the left. I kind of think it's kind of nifty, but what's in the middle is very easy to follow. We're just following a pattern, and at the bottom of that pattern, we can see that negative times negative is positive. Here's one that's a little more visual. Some of you might like this. Some of you might like something else that we've done here. But what we're going to look at here is something that's sort of physical in nature. So let's say I have a water tower. Forgive me, art's not my strong suit. So I've got this water tower, and there's a certain level of the water inside it. And what we're going to do is we're going to say that this water tower is leaking. So what that means is the water level in this water tower is going down. So the level is going down, and I'm going to call that negative because the water level is going down. That's negative. Then what I'm going to do is I'm going to back in time. So I'm going backwards in time. That's negative. And then what happens if I go backwards in time, the water level is going to go up. And so it was leaking, but I go back in time, the water level goes up. That's positive. So negative times negative is positive. You might like that one. You might like the pattern. You might like the symbolic manipulation over on the left. Any of those can be a way to sort of describe why is a negative times a negative give you a positive answer. Okay. Scientific notation, something a little more concrete for us now. Scientific notation is a shorthand way to write really big or really small numbers. The way that we always write scientific notation is we put in a decimal after the first non-zero number from left to right. So here's what I mean by that. And I'm going to use some relatively small numbers that we wouldn't technically use these for scientific notation, at least the first one, but we're going to just to illustrate the point. Let's say I wanted to write the number 273 in scientific notation. Now you wouldn't, you'd just write 273, but just to illustrate the point, what I'm going to do to put this in scientific notation is I'm going to put in a decimal after the first non-zero number as I go from left to right. So I'm going from left to right, I'm going to put it right here. So when I write this in scientific notation, I'm going to have 2.73. I'm going to use powers of 10 to help me write this number. So it's 2.73 times 10 raised to some power. What this number is going to look like in scientific notation is this here, 2.73 times 10 raised to some power. What I have to figure out is what power am I going to use? And there's a couple of ways that students manage this. One is to think, what do I multiply 2.73 by to get 273? I'd have to multiply by 100, so that's 10 to the second power. That's one way, probably not a very common way. Another way is, how many places did we move the decimal point? Well, the decimal point used to be here. I moved it 2 places, and so this needs to be 10 to the second power. So what I have here then, if I want to write 273 in scientific notation, it's 2.73 times 10 raised to the second power. This can also be used for small numbers, like, for example, 0.00517. Now, this one you might actually put in scientific notation, and we're going to do the same idea. We are going to find the first non-zero number from left to right. That's where our decimal is going to go. So our decimal is going to go here after the 5. So it's going to be 5.17 times 10 raised to some power. Now, the question that I'm going to ask myself to figure out what power to raise this to is 5.17. What do I have to multiply by to get 0.00517? Well, that's a weird one. Well, we're moving the decimal point 1, 2, 3 places. So there is going to be a 3 in this exponent. Here's the thing, though. This 5.17 has to get smaller to become 0.00517. Since that's true, we're going to use a negative exponent. And the idea here is we're actually dividing by 10 to the third, but we're going to write it as multiplication because that's how scientific notation works. And because we're wanting to divide by 10 to the third, we'll multiply by 10 to the negative third. And so in scientific notation, that number would be written as 5.17 times 10 raised to the negative third. One thing I want to say before I have you practice a couple of these, some students are good memorizers, and they memorize this by saying, well, if I move the decimal to the left, I'll use a positive exponent. If I move the decimal to the right, I'll use a negative exponent. There's nothing wrong with that. That's perfectly fine. I'm not really a big memorizer, so the way that I would think about this instead is, okay, now I have 2.73. I need to turn that into 273, so this needs to be a positive exponent to make my number bigger. I have 5.17. I need to turn it into 0.00517. I need to make this number smaller, so I'll use a negative exponent on my 10. And either of those that is better for you is the way you should try to remember it. Do you have any questions on taking a number and writing it in scientific notation before I have you try one? All right, here goes. I want you to write that number in scientific notation. It'll take me longer to type this than it will for you to do. I'll make a poll. Hang in there with me. Okay, so rewriting that in scientific notation, what's it going to look like? And off the top of my head, I don't remember if the quiz or the exam asks you to use X for multiplication or an asterisk for multiplication. Follow the instructions that are on the quiz or the exam when you do that. If you put an X and it's supposed to be an asterisk and it scores it as incorrect, just send me an email and I'll fix it. But do your best to follow whatever instructions are given. Off the top of my head, I don't remember if it's a X or a asterisk for multiplication. All right, we'll go another 20 seconds, and then we'll talk about this one. All right, let's see what we've got here for this one. Okay, strong agreement, not unanimous, and there's a couple in there that are easy to talk about, so we'll do that. Okay, so to put a number in scientific notation, what we're going to do is we are going to find the first non-zero number and put a decimal after it. So when we do that, we're going to the first non-zero number, which is that 4. We're putting a decimal asterisk, so we're going to have 4.13. And that's going to be multiplied by 10 raised to some power. And then how did the decimal move? Well, it moved 1, 2, 3, 4, 5, 6, 7, 8 spaces. So we're going to have an 8 in the exponent. We just have to decide if it's a positive or a negative 8. Well, I'm taking 4.13 and I'm turning it into this huge, gigantic number. I need it to get bigger, so I'll use a positive exponent. So 4.13 times 10 to the 8 is how we would write this in scientific notation. One thing I do want to say about 413 times 10 to the 6th, it's true that that does have this same value. The problem is that this isn't scientific notation, because in scientific notation, we put a decimal in after the first non-zero number. So that's, while this does have the correct value, it's technically not scientific notation because we put a decimal in after the first non-zero number. Cool, that's why I said it, Laura, perfect. All right, try another one. Rewrite this one using scientific notation. I'll make a poll for this. Again, it'll take me longer to make the poll than it will for you to do it. Okay. I think I've got them without typos, I'm pretty sure. We'll go another 20 seconds, and then we'll talk through this one. All right, let's see how we did here. Okay, not unanimous, but strong agreement. Very good. Okay, that's good news. So we want to put this one in scientific note, and I think I understand what the problem was for the couple people that answered differently, so we'll address that when we talk about it. So when we do this one, we want to find the first non-zero number, put in a decimal after that. So this is going to be 3.141. We're going to keep all the decimals. We're not always going to keep 2. The examples that I did at the beginning just had we just went to the hundredths place. Um, and that's part of the reason I put this example in there, is so that we have a chance to talk about the fact that whatever decimals are there, we keep them all. If it's just one, great. If it's two, great. If it's three, great. If it's four, we keep them all. So the decimal point goes in after the first non-zero number, and we keep everything else after it. And then this will be times 10 raised to some power. We got to look at how the decimal point moved, and it moved 1, 2, 3, 4, 5 places. And then we just have to decide if that's going to be positive or negative. Well, I have 3.141 that I need to turn into this really small number. So I need to raise it to 10 to the negative fifth power. And then so that's what our number will be in scientific notation. Scientific notation is usually a topic that goes really well for students. It's important that we discuss it because it may be relatively new or it may be really old for you, something you just haven't seen in a long time. I'm just going to let you try to solve this problem. A half-gallon container of juice contains 64 ounces. How many 6-ounce glasses can be filled from this container? And then a poll part of this I'm going to do is the second part. How many ounces of juice are left over? So that part's going to be in a poll. The second part, how many ounces of juice are left over? And this is one I guess you could do with the area model, but you probably don't want to draw 64 circles to represent the 64 ounces. So we'll do this one just by dividing. And I want you to have an answer for both questions, but the one that's in the poll is the second one. How many ounces are left over? We'll go another 30 seconds, and then we'll do this one together. All right, let's see how we did. Unanimous. Outstanding. This is one that usually trips students up a little bit. Really good. I'm thrilled with that. Okay, so when we look at this, we have 64 ounces and we're filling up 6-ounce glasses. So to figure out how many glasses can be filled, we'll just do 64 divided by 6. And when I do that, 64 divided by, 64 divided by 6, I get 10.666, and that keeps going. So how many glasses can I fill? That's 10, and my expectation is everybody had the 10. And then the second part of this is the dangerous part, but nobody got tripped up. I'm thrilled. How many ounces of juice are left over? It's not uncommon for students to just look at this remainder over here and say, well, there must be 6 ounces left over. But we know we're going to disregard that. This is kind of like converting numbers between bases and all these we've seen before. We're throwing that out and we're going to say, okay, wait a minute. If I fill 10 6-ounce juices, that's 60 ounces. There were 64 when I started. I've used 60, so there are 4 ounces left over. And you did great. Normally this trips somebody up and it didn't. Normally it trips a lot of people up and it didn't. And we're throwing away this decimal remainder. We're not going to use that. That's the important part here. All right, here's a question that reads pretty challenging, but then falls back to being something that we've done, although a little bit of a long time ago now. A boat travels downstream at 8 miles per hour and upstream at 4 miles per hour. What's the speed of the current? And what's the speed of the boat with no current? Now, these are relatively simple numbers in here, but I want to go through the process of doing this no matter what the numbers would be. And so the way that we're going to look at this is we're going to call B the speed of the boat, and we're going to call C the speed of the current. When I'm going downstream, the current's pushing me, it's helping me. So I have the speed of the boat plus the speed of the current is 8 miles per hour. And then if I'm going upstream, the current's working against me, so it's slowing me down. So the speed of the boat minus the speed of the current is 4 miles per hour. And now I have two variables, two equations, so I can solve this. And I'm going to use substitution to do it. In that bottom equation down there, I'm going to add C to both sides to get B by itself. These will cancel, and I can see that B is just 4 plus C. Now I'm going to substitute, and this is from a long time ago, but it's really good for us to be reviewing it today, which you'll see in a couple of minutes. We'll revisit this. But B is the same as 4 plus C. So wherever I have a B in the other equation, I can put 4 plus C in there instead. And so I'm going to have 4 plus C, that's where the B was, plus C equals 8. Now I can simplify, and this is C plus C is going to be 2C. C plus C is 2C, so that's 4 plus 2C equals 8. Now I want to solve this equation. We haven't done algebra in a while, so it's good to do the review here. I'm trying to get C by itself, so I want to get the term with C by itself. So I need to get rid of that 4. To get rid of that 4, I'll subtract it, which I need to do that on both sides. Those cancel, and so I have 2C is equal to 4. Oops. And then the last thing I need to do is divide both sides by 2. Here they cancel, giving me C. 4 divided by 2 is 2, and now I know the speed of the current is 2. And so this question had two questions built in. What's the speed of the current? I just found out that that's 2. And then the other one, what is the speed of the boat with no current? Well, that's what I called B, and over here I can see that B is just 4 plus C. So now I know that's 4 plus 2, and so the speed of the boat with no current is 6 miles per hour. Let me know if you have any questions on anything in there. We haven't done solving two equations like that in a while, so if it's a little rusty, that's okay. Hopefully this fixed it up for you. But if you have questions, I want you to ask them. Okay. Just a little review of working with integers in sort of, please excuse my dear Aunt Sally, order of operations type of situation. Nothing too involved though. The first one is if we have negative 14 plus 36 over negative 11, the key here is whenever you have a division bar like this, what that is, and you don't have to know it this way, but it implies parentheses around the top and parentheses around the bottom. Essentially, whenever we have a division bar, the way that I like to say it is do everything on the top, do everything on the bottom, and then divide last. And that's what we'll do here. So if we want to simplify this, we'll do everything on top. Let's see, that's negative 14 plus 36 is 22 over negative 11. And then we'll have to divide. And just like multiplying positive and negative, When I have one of each, I end up with a negative answer. Dividing is the same. So here, 22 divided by 11 is 2. Positive divided by a negative is a negative. And so we end up with -2 as a solution to that one. Another one to look at is if we have -5 minus 9 divided by -7. So this time we don't have a division bar, but we kind of do. We have that division symbol in there, but we have parentheses. So we know we're going to do everything in parentheses first. -5 minus 9, that's going to be -14 divided by -7. And 14 divided by 7, that's going to be 2. Negative divided by a negative. Works the same way as multiplication. Negative divided by a negative is going to be a +2. Let me know if you have any questions on that. I figured that's pretty straightforward. Most students are really comfortable with that, but just in case. All right, and the last thing I want to say about section 4.4 is when you work on the problems in 4.4, there's a little bit of modeling review in there where you've got a real world situation and you'll create an equation for that. We kind of did that in the boat problem just a couple minutes ago, where we have a real world situation and we make an equation for it. Okay. Anybody have any questions about 4.4?